This is about one line and a bit up. This is about 2 lines up. When they meet in the middle, they should add. They're going both above, they should add. And sure enough, in the middle, we get a wave. That's the sum of both. About 3 lines up. Again, once they pass by, though, it's as if nothing happened. You can see the bigger waves now on this side, smaller ones on that side. That's the idea of interference. They interfere at that point and then move on.
And the white dwarf is actually stealing matter from its companion star, like this image and like this GIF shows. You see, it's stealing matter that's slowly spiraling towards the white dwarf, forming an accretion disk of matter around the white dwarf that's spiraling closer, heating up as it does. Well, I also found this video that helps demonstrate the process, so I'm going to bring it in and let's take a look. Because what we have is, again, this cloud. You got the white dwarf stealing matter from its binary partner and building up, and it's getting hotter and hotter. And what happens? All of a sudden, that matter will fuse.
This is our nice, not-so-round Earth, tilted. And then it's orbiting, you know what, let's make me the sun. Why not? That's kind of fun. So it's rotating on its axis. It's also rotating around me, and it's just on an angle. This rotation is angled relative to the path it takes around me, the sun. Yeah. Bet none of your other profs get to claim they're the sun. So what do we have here? This is our axis of rotation, the virtual spike through our planet. This is just another line to keep us in perspective. It's going to be not moving. It's just straight up and down to remind us which way is up and down. And this is what is happening. Earth is spinning on its axis, and that axis, the big metal spike, fake metal spike, of course, is itself rotating.
And we were told in the question the distance from the planet to the sun, or A, is 3. But we don't care about A. We care about A cubed. So we need to know what A cubed is. So right away, I can think A cubed. Remember, that's just 3 times 3 times 3, or 27. Punch in our calculator, we should get 27. All right, so what happened? This ball exerted a force on this one. But when that happens, this ball exerted a force exactly back on it, which actually is why it stopped. Again, the whole idea is we should have 4 going out the other side. And that's why it just keeps alternating back and forth. Of course, if we really want to, we can do all 5. Yeah, I mean, at least some people are laughing, guessing what already is going to happen. Don't be too excited. Yeah, it swings back and forth, of course. Yeah. That being said, we can start being more creative, too. You can have things like this, where you pull 1 from each side, and they keep having the other side go. If you really want, you could do 2 from each side. Oh, and it all gets tangled up. That's not part of the demonstration. All right. You can do 2 on one side, 1 on the other. And you can see it alternates which side is 2. What's going in should be coming out the other side. Feel free at the end of the lecture, come on up. You'll be in my office too if you want to test it out. There is only set levels between these 2 points. Set lines that I can be at. So-called quantized energy levels. That's really, they make it sound more complicated than it is. It's just different lines, different places where it could be, different orbits where this electron could be. And it has to get exactly the right energy to go from one to the other. If you look at it, it seems like a pen all of a sudden is disjointed. It seems a break in the middle. It's not. It's still just one big solid pen, but it looks like there's a break in it. And that's because the light is bending. What seemed to happen? Anyone see something?
That's so weird.
Yeah. Yeah, she spun a lot faster when she brought her arms in. In fact, if we want, we try and do it again. Arms still good?
Yeah.
All right, let's try it one more time. And let's cross them. Same thing happens with figure skating. This is why figure skaters, when you see them, they start to spin and they cross their arms or cross their arms above their head. They're making their mass much more centralized and they spin faster. That's the idea of conservation of angular momentum right there. And the force of gravity from the sun is the yellow arrows. And what we'll notice is when they line up, we're going to get the biggest tides. This is going to be much larger at this point. In fact, we're going to see it in a second. The tide's much larger. We'll talk about why it's slightly off-center in a second. We now think there is liquid water below the surface. It's not just a debate, was there water? It's now, is there still water? And in fact, we think there is. You can see it's encapsulated in a shell. This was because it's going to go into the atmosphere. It's going to have friction with the atmosphere, just like anything going into our atmosphere. So this shell was protecting it, and we'll see in a second. Otherwise, it probably would have gotten melted or at least damaged. And then the shell gets popped off. Now the sensor goes down in a parachute, and it made it about 150 kilometers down, I believe. So it gave us an idea of what the upper layers of Jupiter's atmosphere were like. You can see right away, Charon and Pluto right here are tidally locked. You can see they're both keeping the same face, the white dot, towards each other. The other moons, not at all. They're not tidally locked. This one's going kind of crazy. So you can see little jets of matter. Don't look like much, but they're still pretty violent. They erupt out, get pulled back by gravity. This is just looking at the sun in normal, everyday visible light. And if I wanted to, I could show where the sunspots are. Could probably have guessed it's the little spots on the sun, logically enough. We'd also show where the magnetic field is strong. Also, not exactly a surprise. We said it's going to be strongest near these sunspot pairs, so yeah, it makes sense. Great. Well, what is this really going to show? Let's look at X-ray. Remember, X-rays are a much shorter wavelength, much higher frequency, much more energetic part of the spectrum. So if we look at the sun in X-rays, it should give us an idea of where the more energetic areas are. Sure enough, they are right near the sunspots. You can see there is violent eruptions taking place. There is violent activity occurring near the sunspots. So we're going to see it is an explosion. A violent explosion ejects matter. We can watch it a bunch of times. And boom! An explosion. All right, one more. I think this one I shared in the resources. You can watch it a ton of times if you want. As it zooms in, it looks like a solid ring from the outside. It's not until you get very, very close in you'd be able to actually pick out the little individual chunks of rock and ice. And you can see this video does show something very nice, that they all seem to flow in the same direction.
Well, my pen is a fixed size. It's not going to change. I'm not magic. This pen is a pen. What happens as I move it towards the camera? Seems to be getting bigger. It's not, but all that's happening is its angular size is changing as its distance from us, the viewer, changes. So this is me. The angular size of my phone from this perspective would literally just be the angle it takes up when looking from one side to the other. So this we could define as the angular size. I could even give it a fancy symbol theta. And that's just the size this object takes up from this perspective. What happens if I move my phone, though? Relative, so I'm still standing here. Go paper, two-dimensional me. Now my phone has moved closer. Okay, now the angular size has changed. The angular size would be this distance. Theta 2 I could even call it if I wanted to. Nothing changed. I'm still at the same spot. This phone is still the same size phone. It's just because of its relative position, it now seems larger to me. Which again is the very long way of doing this demonstration I did right here. But hopefully that actually demonstrates the idea. And please ask questions if not.